Let's discuss the stationary waves on a clamped string. We have already discussed about the formation of a stationary wave in a clamped string in one of the sections earlier. Say we are given with a string of length L, and if we just pluck the string in between and we release, we can see that the string, due to its elasticity, will start oscillating in such a way that the two ends where the string is clamped will behave like nodes, and the medium particle exactly midway between the nodes will act like antinode. Other particles will also oscillate with the smaller amplitudes. Now in this situation, the string is oscillating in such a way, we know that the separation between two adjoining nodes is written as lambda by 2. So here this length L of the string will be lambda by 2, which will give us the wavelength of the wave in this string, which is 2L. If we find out the oscillation frequency of the oscillation of a string, this frequency can be written as V by lambda, and here the wavelength is 2L, so we can write it V by 2L. And as we know, in a stretched string, wave velocity can be given as root of T by mu. So this can be written as 1 by 2L root of T by mu. And once established, the wave will be sustained if there is no energy loss in the media. Now, if we just increase the frequency of oscillation, the wavelength will decrease as the speed is a constant. Say, if we talk about another mode of oscillation of a string in a stationary wave, that is possible if this loop is increased. So, if we just give a support at the middle point and we oscillate a part of a string, automatically we can say the oscillations will be transferred to the remaining part, and that will also start oscillating. In this situation, the total length is equal to the separation between two alternative nodes. So in this situation, this length can be written as lambda, and in this situation, if we find out the oscillation frequency V by lambda can be written as V by L now, which is just in terms of the initial frequency. If we write it as 2 by 2L root of T by mu. If this frequency is written as N naught, this can be written as twice of N naught. And we can say this is a situation when the wavelength is maximum. If we increase number of loops in the string for the oscillation of a stationary wave, the wavelength will decrease and frequency will increase. So this is the situation where the wavelength is maximum. So this is the minimum possible frequency at which the string can oscillate in form of a stationary wave, and this frequency is called fundamental frequency. This fundamental frequency of oscillation for a string for the formation of stationary waves. And this is the oscillation of a string in which the frequency is twice the fundamental frequency, which is called second harmonic frequency. And as in the previous sections we have studied that above a certain minimum frequency, all possible frequencies in a given instrument are called overtones. So after this frequency at which stationary waves can be obtained in the string is twice the minimum frequency. That's why it is called first overtone. Because there is no possible frequency between N0 and 2N0 at which stationary waves can be established here. And if we talk about the next possible frequency, that will exist when there are three loops in the same length of a string with the clamps located at nodes. So situation would be this. Now in this situation, the length of a string can be written as 3 lambda by 2, as each loop length is lambda by 2. Now we can see the lambda wavelength can be written as 2L by 3, and in this situation oscillation frequency can be written as N is equals to V by lambda, which is V upon, this can be written as 12 by 3, which is 3 upon 12 root of T by mu, which is 3 times the fundamental frequency, which is called third harmonic. I hope you can recall earlier we have studied that all frequencies which are the multiple of the minimum frequency of any instrument are written as harmonic frequencies. And after this frequency, next frequency is this at which stationary waves can be established. That's why it is termed as second overtone. Here you can easily understand that if there exists a frequency between these two, then at that frequency the wavelength will be such that on the two clamps notes will not be obtained, and if notes are not obtained at the clamps, the particle of a string which is tied up at the clamp must oscillate, which is not possible. That means the string can sustain a stationary waves only at frequencies which are multiple of fundamental frequency. So this is N0, this can be written as N2, this is N3, because this is the second harmonic frequency, this is the third harmonic frequency. Similarly, we can also talk about pth harmonic, in which say a string oscillates in p loops if large number of loops are obtained in this manner. So we can say this 1, 2, 3 up to p minus 1 p loops are obtained. In this situation, the length of a string can be written as p lambda by 2, or wavelength can be written as 2L by P. Now in this situation, if we talk about frequency, it is given as NP, which is V by lambda, or it can be written as PV by 2L, or it is P by 2L root of T by mu, and the frequency is P times the fundamental frequency. As there are P loops, the frequency of oscillation will be P times the minimum frequency, and it is termed as pth harmonic. And if we just count the number of overtones, this will be P minus 1th overtone will be there, as there are no frequencies at which stationary waves can be obtained in a clamped string other than these frequencies. So when a clamped string is made to oscillate at any of these harmonic frequencies, stationary waves are established in the string, which will sustain and carry on if there is no loss of energy. Let's write down the concept of formation of a stationary wave in form of a node, in which we can state in a clamped string, stationary waves can be established at any frequency which is multiple of its fundamental frequency. If we supply energy at a frequency which is multiple to the fundamental frequency of a clamped string, the particular harmonic or overtone will be induced in the string. Let's discuss with the help of an example, like say we are given with a string of length L. We find out its fundamental frequency N0. This can be given by V by 2L. And say if we substitute the wave speed in this string and length, say for example it is 10 Hz. It can be any value. Just for example, I am taking, say if it is 10 Hz, and I bring a tuning fork, which is the source of oscillation, and the frequency of tuning fork is say 30 Hz. And if the fork is brought close and it is just connected to clamp or a string through which the oscillations can be transferred, and say if the tuning fork is oscillating at frequency 30 Hz, the clamp as well as the string will start oscillating at frequency 30 Hz, and at this frequency automatically the wavelength will be established in such a way that there will be 3 loops obtained in the string, and it will start oscillating in form of a stationary wave with 3 loops, because it matches with the third harmonic of the fundamental. If the tuning for frequency would have been 50 Hz, automatically 5 loops, string will start oscillating in 5 loops in such a way that the frequency of a string will be 50 Hz. Now, this is the way by which we can say we are inducing various frequencies in the string. Here the string is also oscillating, ns can be written as 30 Hz. And this is the way we can say we are inducing harmonics. This phenomena is called induction of, as we are inducing third harmonic, we can write it as induction of third harmonic in clamped string. In this manner, we can induce any harmonic oscillation in the string, or a string can be made to oscillate in stationary waves of a desired frequency by using an external source of matching frequency. In next section, we'll discuss the same concept in detail, which we term as resonance in clamped string stationary waves.